Hello, welcome. So in the previous episode, we implemented conditional skips within the processor. And so we have an if-eq instruction, which will set a skip bit on the next instruction to skip it if we don't want it to execute. So that's working quite well, and actually it simplified the test cases quite a lot. So off camera, I updated some of the test cases, which are all running and passing. So in the CPU def, I implemented all of the different instructions that we have for skipping. I also updated the error and halt instructions. So the opcode has changed slightly for those. And also now there's an error instruction, which actually comes in quite handy. So if you see in the jump test case, for example, we can just litter it with these errors. And if it hits an error, it will fail the test case. We can also do that in these test cases where if the condition fails, then we just error instead of having to jump to an error at the end of the test case, which is kind of nice. So it does clean things up. So the CPU def has been updated, and you might notice that there's a lack of certain instructions. For example, how do you do greater than because you only have greater than or equal? Well, that's a very good question. The answer is pseudo instructions. So if you want a greater than, all you need to do is a less than with the operands swapped around. So greater than A comma B would be less than B comma A. Because if you think about it, that kind of makes sense. Similarly, you can't swap the immediate around. It's always on the right-hand side, but there's a trick that you can do if you want greater than. You just increment the immediate. So if you think about it, if you want, check if a register is greater than 4, that's equivalent to saying greater than or equal to 5, right? And you can do the same thing with the unsigned variant of greater than, which is called high. It's just either low with the operand swapped around or higher or same with the operand incremented. Same thing with less or equal. There is no less or equal instruction, but you can synthesize it from greater than or equal, or you can synthesize it from less than. And lower or same is the same. So moving back to the processor, some more off-camera updates that I made were I updated this, so it now has all of the implemented conditions, and I removed the branches from here because they're no longer implemented. I also added the error here, and I moved the halt from where it was to here. And there was a bug that I found when I was updating the test cases. So I updated the test cases in several places. In here, these ones were updated. And I did find that the halt logic didn't work quite right. What I needed to do is move the enable halt from only caring about the stall line to also caring about the skip. That way you can skip an error, for example. Otherwise, the error line would still activate. So we see enable write here and enable halt as well. So what I'd like to cover in this episode is microcode. What is microcode? Well, actually, we've already been using microcode a little bit. If you look in here, this is microcode, or a form of microcode. It's basically just a lookup table that's stored either in ROM, or you can have a ROM-like thing out of multiplexers, like we're doing right here. So essentially, this is microcode. And in fact, there's also microcode in here. So this is microcode. This is just looking up the ASCII value. So you can think of the ASCII value in here as being the opcode, and the different segments to light up as being the control signals that come out of here. So that's essentially what microcode is. It's just a ROM with a bunch of lookup tables that emits some control signals. So why would we care about microcode in this processor? I mean, if you look at it, the control unit is pretty simple right now. There's not really a huge need to convert this into microcode. But the issue is that, yes, this is simple right now because I have hardly any of the instructions implemented yet. But this is going to grow in complexity quite a lot. And at some point, this is going to be really difficult to work with, especially if we need to, say, rework all of the opcodes. Then we need to change all of these AND gates. We have to think, what is this AND gate even doing? I know it's matching part of the opcode, and it's sort of readable, but also sort of not. So if we switch to microcode-based control logic, where we just have a big ROM that we're looking up the control signals from based on the input, what would that even look like? How do we make it so that it's really easily readable? Well, let's dive into that a little bit. One of the things that we could do is we could use customasm to build our microcode ROM. So there's a few different ways that we could do this, but essentially it's just an instruction that takes a value. And what do we want to do in here? Well, I think the simplest thing is just to actually emit the value, right? And I don't think we have 16 bits, but let's just presume that we do. So maybe we only have a single instruction. Let's call that instruction done for now. So this is just an arbitrary instruction just so that we can use this. So if we have a lookup table, then the address coming into the lookup table will be our opcodes. So NOP, for example, would be the first opcode, and it does nothing, basically. So we could potentially also have a version of this that takes no parameters. So then we could just go done. Okay, so this is address 0. Next we have, I think, rets, and that's not implemented, so that's the same as a NOP. And then after that we have halt and error. Well, if we have a halt, what do we want to do? Well, we do need to pay attention to the enable halt here. But what if we didn't need to? What if we refactor this a little bit and say input 5 goes away? And what we could do is we could add an input to these that has this. So then in this arrangement, we don't have to care about the enable halt. We just have to emit a halt or an error and presume that the enabling will happen elsewhere. And in fact, we could refactor this so that these are just AND gates on these outputs from the control unit. So then we just need to raise these lines. How would we do that? Well, maybe we just do this, right? And then what is the halt line? Well, maybe the halt line is the first control signal that comes out of this. So that would be just 1, I guess, right? So then maybe the error line is the second bit. So maybe we just define it like that. I think that would work. So then error is just this. Well, first of all, let's compile this and make sure that it actually does compile. Okay, it doesn't like the duplicate symbol. There might be a way to get around that. Oh, that does compile. Okay, so we have a NOP, then a NOP, then halt and error. Well, let's send that to a file. All right, so we have a hex file. So we could have microcode, data bits, let's say 16 for now, and 5 address bits. In here, we want to reload it on model start. Number format, I'd say, let's make it binary. Edit, load. Let's load our microcode. So we have our bits in here. So we have microcode. What should we do with it? Well, we'd like it to replace our halt logic here. So most of this would disappear. So currently we only have 2 control bits implemented. So we'll just put inputs 16, but just 2 outputs. The first one is halt. Let's set these back to 2 inputs. There we go. And there we go. Now, this should work. It doesn't. Why would that be? Oh, do I have them backwards? Looks like I have them backwards. Well, that's easy enough to fix. We can go to here and then rebuild it. And our tests pass again. Do all tests pass? Yes, they do. So that's one advantage to microcode. In order to fix it, I just swapped these around and recompiled. I didn't have to figure out what to do with the hard-coded logic in order to fix it. So this does speed up development, which is nice. So what can we do next? Well, we could try and do the jumps. Jumps are at 1, 2, 3, 0. Okay. Well, I believe this is how you specify that the next thing is at this specific address. So jumps are at 1110. So jump like that. And then we just add our jump in here. And we want this to be the 3rd bit, or bit number 2. All right, that seems to have worked. All right, so the next bit in here is jump. Let's check our tests. Oh, okay, that did not work as we thought. What's it doing? The jump bit is not going high. Let's make sure that our microcode is correct. It doesn't look like it. Okay. Times 16, I think that's what the problem is. We could probably troubleshoot this. The address is that. Does that make sense? No, it does not. All right, I think we just don't need this. I think this is correct now. 1C, that looks better. Yes, that is correct now. Okay, so we now have microcode implementing halt, error, and jump. What about all of these ALU ops? Well, we can look into that. So we just need to handle this logic here. So we need 3 bits output for the ALU op. And actually we have only 3 instructions for that. So how would we do that? So NOP or no ALU. Let's call it no ALU. That is 7 shifted over 3. And then we have add, which is 0. And then we have move, which is 6, I believe. Now, what is the instruction? The highest bit is a 1, and then the next bit is a 0. So the first thing we have here is add. Then we have nothing. So I'm just going to denote those with placeholders for now. Well, this is our move currently. Well, this is our like that. Oh, right. Let's just call this no alien. So in our control logic here, we can output 3 bits, and we can say that that's our ALU op. Move things around here a little bit. All right. Yes. So we have special cases for all of these, and the ALU op is not 7 like it's supposed to be. And here it's supposed to be 3. Interesting. Interesting. So how do we fix this? Well, it's kind of unfortunate that the no op for the ALU is 7 instead of 0. Means in order to fix this, we'd have to probably say done is actually ORed with so something actually along the lines of this. So this could work. Sort of. So these all seem to work. This, yeah. Wait, how is this working? I guess it is. Okay, but these are not correct. So we can make these 2 pass by having 3, or just modifying the test cases to something that's actually implemented. And instead of 3, let's set it to 6. So those ones are working, but how do we handle these? Because it's saying some random instruction should have a no op in there. Well, we could instruct the assembler to fill memory with a specific value, specifically the no ALU value, so that by default that's what memory would contain, but it would be easier if memory just contained 0. So what would be a lot easier is if we did this, and then add was 1 instead. And then we can undo this change because we don't need it. And then we can just go done again like that. So this would be a lot easier. Can we do that? Well, yeah. Oops. In our execute unit, we do this. Let's just move this out like that. All right. So let's make sure this works. Okay. Yep. So then do our test pass. Not quite. Our tests are expecting the no op for the ALU to be 7, and it's now 0. And we need to fix any case where it's assuming that. So let's do that. So our add is now 1, and our NOP is now 0. Well, we'll fix this in just a moment. I think that was everything. Yeah. Okay. So this disappears. So now what? Well, we just have memory access left. What do we do with that? Well, looks like we're matching the instruction. It's all ones, which is helpful. And then the lower bit decides whether it is a store or not. So, okay, this looks pretty easy. Let's rename this store. Okay, well, we know that this is here. We have load. And we want to control two different lines. Well, let's just do this. And yeah, we have mem. And this one, this one's width 3, so we have to increment by 3 to get the next slot. And then we have store, that's 7. And then we have, let's just say, or mem. Don't think that's going to work. How do we handle this? Making it a subrule def doesn't really work. We could capitalize these. Let's do that. Okay, so then value here, and then and then mem or store. All right, that seems successful. So then if we have mem and store, okay. All right, tests are finally passing. Okay, run all tests. What? Save. That's better. Front panel had a problem. All right. All right. Had this problem before. Don't know how to fix it. Now that seems to work. Load store failed. Aha. Well, that's because we're now not adding when we're doing a memory op. So actually what we need to do is add. Oops. Now these tests pass, but the memory access one fails because we just changed the add. So the ALU op here is now 1. And that now passes. Awesome. For now, I'm not going to worry about the skip or stall logic. I'm just going to leave it as is. So we now have microcode, and the microcode is fairly malleable. If we need to change the logic, we just go in here and we just change it here. Yeah. And adding new control lines is super easy. We just figure out what the width is, and we can just shift it over the correct number of bits to put it at the right position on the output of the ROM. And yeah, that's the major reason to use microcode, is it greatly speeds up building all of the logic for the control unit. So let's see this running. It's running fine. Yep, everything is running again. So that's it for this episode. Thank you very much for watching, and I hope you have a great day. Bye.